will see how to use this equation to solve our problem. So firstly, have a look at this question. Try to define this problem. What information can you collect? And here you can see there is an unbalanced flywheel, and we already know the mass of this flywheel is 25 kilo. Unbalanced flywheel, that means the mass is not uniformly distributed in this flywheel. And we already know the radius of gyration. So that means we can easily use this radius of gyration to calculate its MMI about axis through the mass center point G. So initially, if you connect O and G, a line connecting O and G should be horizontal. Initially, this flywheel was at rest. Okay. So release it, then because the mass center point G is here, and this flywheel at this moment is not balanced. So you will get a rotation. By observation for this easy problem, and you can see the rotation direction should be clockwise. Okay. The target here is to determine the horizontal and vertical components of reaction at the pin O. Okay, as I mentioned when we watched the video of oil pump, I said if this flywheel or the crank in the oil pump is in static, it should be easy to work out the reaction force at the pin point O. Okay, it should be very easy. Okay, this reaction force should be equal to the weight. Okay, the weight of this flywheel or the crank in the oil pump. But now, what will happen? Okay, let's have a look. Okay, let me switch to another camera. Okay, so we have already defined this problem, and we know this should be a rotation about a fixed axis. And in this problem here, okay, we can have a diagram, and in this diagram here, we have the rotation center. Rotation center is also the circle center of this flywheel. And we have the mass center point G is here. Okay, now for the free body diagram. Oh, sorry. Before I draw the free body diagram, I should let you know the defined coordinate system. Okay, so for this problem, this is a rotation about a fixed axis problem. For this problem, I'm going to use normal tangential coordinate system. Okay, and in this one here, I define normal component positive direction to left side, and positive tangential direction downward. Okay, for a problem at this instant. One thing different from x, y coordinate system is when you define x, y coordinate system, okay, x, y, z. Okay. If z positive z direction outward, perpendicular and outward to this paper, then using right-hand rule, you see the positive direction will be counterclockwise. But if you define the positive z direction is inward, then the positive rotation direction will be clockwise. In this normal tangential coordinate system, it's a bit different. In this one here, when you determine the positive normal direction and positive tangential direction, and then the positive rotation direction is already defined. Okay, so for example here, normal direction to left side, we imagine there is a rotation center along this line somewhere, okay, for example here. And the tangential direction downward, then that means the rotation direction in this positive rotation direction in this defined coordinate system must be clockwise. Okay, it's already defined. Now, in this one here, let's have a look. In this free body diagram, we should have OT, okay, along T direction. We have a component of the reaction force at the axis of 0.0. And we also can indicate ON. So in this one here, why I put ON to left side? Because in this one here, you can see ON is unknown, and we already defined left side is the positive normal direction. So I indicate ON to left side, assume it's positive. Okay. But for OT, by observation, you know OT must be upward. Okay? But in my calculation, because OT at this moment is unknown, okay? So in my following calculation, I like to assume OT is positive. If I assume OT is positive, according to this coordinate system, because downward is the positive T direction, and then that means in my following calculation, I assume OT is downward, okay, downward, positive. In my following calculation, I will use this assumed positive direction of OT. To remind myself for this OT direction, positive direction assumed, I use the dashed line. I use the red color, okay, to remind me this is just an assumed positive direction. Now, for gravitational force, here, W, or weight force, W. Of course, for this one, because we already know the mass of this flywheel, so we can easily calculate the magnitude of this weight force, and we know the direction of weight force must be downward. Okay, so this means W in this coordinate system should be positive. Now, for kinetic diagram, in this kinetic diagram, we will need to indicate alpha and AG. AG is unknown, alpha is unknown, so I just assume these two positive. So for IG alpha positive should be clockwise. Okay. For AG we resolve AG into AGT and AGN, okay, two components. Okay. And because at this moment, alpha, AGN, AGT, they are unknown, so I just assume they are all positive, indicated in this kinetic diagram. So that's the diagram, FBD and kinetic diagram we need for solving this problem. Any questions? Any questions? Okay, if no questions now, let's have a look. How to do the calculation. Let me share my solution here. Okay, for the first problem is here. Okay, so in the first step, we have defined this problem, and we already saw the free body and the kinematic diagram. And then we can collect all the already known parameters. We know M, we know Kg. Kg is the radius of gyration about the mass center point G. Okay. And omega. Omega at this instant is 0 because we are studying the instant when we release this unbalanced flywheel. Okay. At this instant, the velocity is still 0. But how about the acceleration? Is the acceleration of this flywheel at this instant is 0 or not? Acceleration 0 or not 0? How do you think? No, it's not 0, okay? Angular velocity may be 0, but the angular acceleration won't be 0 because at this instant there is already a force, okay, on the flywheel to drive this flywheel rotating. Okay. Now, unknown, we don't know ON, OT, and alpha. And we can assume all this positive as indicated here, here, and here. Okay, now the calculation. So for solving this problem, we will use these three equations, and because we are using normal tangential coordinate system, so we have these two equations. For the third equation about the rotation component, for this problem, we can use the mass center point G. We can also use the rotation center point O. Okay, in this solution here, the first thing is to calculate the MMI, mass moment of inertia of this flywheel, about the axis going through the mass center point G. Okay, because we already know mg, so this calculation is quite convenient. Okay. Now, along normal direction, have a look. For external forces in this free body diagram along normal direction, we only have ON, okay? So I put ON on the left side. On the right side, there should be MAGN. MAGN because this is a rotation about a fixed axis of 0.0. So AGN, this one, can be expressed using omega square R. And this is from kinematics, and we studied this in week 1. Now, because omega at this instant is still 0, so this means ON at this instant should be 0, okay? So this means the reaction force at the axis is 0.0. The normal component of this reaction force should be 0. Now, along t direction. Along t direction, you will see. Along this t direction, look at this free body diagram. You can see we have two external forces. One is OT, and another one is gravitational force W. W, downward, positive. OT, in the calculation, we assume it's positive, downward. Okay, so in this one here, you can see on the left side, I have OT. We assume it's positive, so I don't need a negative sign before OT. For W, it's positive. Okay, 25 times 9.81. On the right side, there is AGT, the tangential component of the acceleration at point G. For this one, AGT, we know the magnitude is alpha times RGO. Okay. Okay, alpha we don't know. We just put alpha here. The distance from G to O, we already know in the diagram is 0.15. Okay. So now we have our second equation along tangential direction. Now we have OT and alpha, two unknown parameters. And now we will need the third equation for our calculation. This is third equation from this rotation component. We can use point G, we can use point O for our calculation, and in this one here, I provided all the different solutions. First one is to use point G for the calculation. Using point G for the calculation, what can you see? Let's have a look. Okay, so firstly, we need to calculate the moment generated by the external forces above point G. Point G is here. Okay. If we look at the moment generated by all external forces, you can see for W, the moment arm is 0. For ON, the moment arm is 0. And also you know ON is 0. So only OT can generate moment. Because we already assume OT is downward positive in this calculation. So when we calculate the moment generated by OT, you can see it will be counterclockwise about point G. Okay, so this means according to this coordinate system, OT is moment, should be negative. So that's why before this calculation, I have a negative sign. This negative sign is not for OT, but for the moment generated by OT. Okay? On the right side, Ig alpha. Alpha is unknown. Okay, now we have two equations, two useful equations, equation 2 and equation 3. Two unknowns, OT and alpha. Okay. Now, finally, the answer. Alpha is 26.8 radians per second squared. So, this is positive. That means the assumed positive direction for alpha in this diagram is correct. Alpha should be clockwise. But how about OT? OT, you can see the calculation results is negative 144.7 Newton. What does this mean? This means this OT should be negative, upward, according to the system. Upward is negative. So OT should be negative. The assumed positive direction OT is wrong. Okay? OT should be upward instead of downward. The assumed positive direction of OT is only for our calculation, for the convenience in my calculation. And finally, the final result will tell me the correct direction of OT. Okay? Okay, so if you are going to use O, rotation center O, for your calculation, it's okay, and the result will be same. Have a look. In this one here, you can see. We still got alpha, 26.8, positive OT, and negative 144.7 Newton. Okay? So, I'm not going to give detailed explanation on this calculation using O for rotational component. So, for this simple problem, do you have any questions for this diagram, for this calculation process? Do you have any questions? Oh, there's one thing I should mention. When you draw this kinetic diagram, and firstly you assume alpha is positive, clockwise. Okay. If you have already indicated alpha is clockwise positive, then you know, because the direction of AGT, the tangential component of the acceleration at point G, is related to the direction of alpha. So if alpha is counterclockwise, because the rotation center O is here and G is here, so that means AGT, its direction, must be tangent to the circular moving path of point G, and it must be downward. The reason is because alpha is clockwise. So AGT here must be downward. Okay? So this means alpha and AGT, these two are not independent, and they depend on each other. Okay, any questions? Any questions? Okay, if no questions, let me move to the second example problem.